Let's begin this problem session by revisiting the isometries of the complex plane. We have already seen that the isometries of the complex plane which fix the origin are either given by maps of the type T of z is equal to omega times z or T of z is equal to omega times z bar, where omega is in S1. However, there was this condition that omega T should fix the origin to write T in this manner. In this problem, we will give a complete characterization of all isometries of the complex plane. We have essentially done all the hard work. Let's finish the complete characterization through this problem. The first problem is T be a map from C to itself be an isometry. Isometry of the complex plane then show that T is given by either T of z is equal to z0 plus omega times z for z in C, or T of z is equal to z0 plus omega times z bar for z in C, where z0 is a fixed complex number and omega is, as usual, some element in S1, a phase. So as you should guess, the z0, the fixed point z0 can be found out by evaluating t at the point 0. If you look at t of 0, that's the point z0 precisely in both the cases, isn't it? So that's precisely what we will use. Let's give a proof of this statement. The first observation is that if we look at z0, a fixed point which is given by t of 0, and define the map t of minus z0 of z, t subscript minus z0 of z, to be equal to z minus z0. This is a translation by minus z0. If you notice, this is adding minus z0 to z. The first observation is that t minus z0 is an isometry. I will leave that as a check for you. It's quite straightforward. Check that t minus z0 is an isometry. And we already know that if you compose isometries, then we get back an isometry. Then let's do one thing. Let's compose the isometry t minus z0 with our isometry t. And then check what t minus z0 composed with t at the point 0 is going to look like. This is going to be t minus z0 evaluated at t of 0, which is z0 by the very definition here, and that's going to be equal to z0 minus z0, which is equal to 0. Hence, t minus z0t is an isometry which fixes the origin. But we are now in familiar waters, because if an isometry fixes the origin, we know that it is either of the type omega times z or omega times z bar, where omega is some element in the unit circle. Then by the theorem proved in one of the lectures, we have t minus z0 t of z, either t minus z0 t of z is equal to omega times z for omega in S1, or t minus z0 t of z for all z in C. Well, there x is an omega, where omega is in S1. Similarly, this other alternative is that it is omega times z bar, where again omega is some fixed element in S1, a phase. So these are the only two possibilities that we have for t minus z0 t. because we already know what the isometries fixing the origin are. Let's now look at what is tz0 of this. So tz0, define tz0 of z to be equal to z minus z0. So this is again a translation map. This is an isometry. tz0 is an isometry, and further tz0 t minus z0 is equal to the identity map. Yeah, I should just check that this is indeed getting satisfied. They are quite straightforward. And now let's go back to where we are. We are in this box that will be relevant for us. Let's see how. Then tz0 of t minus z0 t. What is this going to be? This is going to be tz0 of, okay, at a point z. Let's evaluate it at a point z. That's going to be equal to omega times z. So either this is satisfied or tz0 t minus z0 t of z is equal to tz0 of omega times z bar. Well, what is the first one? The first one is z0 plus omega times z, and the second one is z0 plus omega times z bar. But then let's try to study what the left hand side is. There are three functions involved, and the associativity of the composition operator tells us that tz0 t minus z0 is going to be the identity, and that will tell us that identity composed with t is t, which is equal to z0 plus omega times z, or t of z is equal to z0 plus omega times z bar for z and c. So we have given a complete characterization of all the isometries of the complex plane. It will be a rotation and a translation, or rather a rotation followed by a translation. Okay, the next problem, we will study the roots of unity. Let's try to study what will be the complex numbers which satisfy the equation of the type z to the power n equal to 1. We are already familiar with z square equal to 1 giving us two roots of unity. We will see that in the complex plane, nth roots of unity can be described in a similar manner. There will be n roots of unity, which we will write down in this problem. So let n be a positive integer. So that the complex numbers or complex number solutions to the equation z to the power n is equal to 1 is given by, solutions are given by z k equal to e to the power 2 pi I k by n for k equal to 0, 1, 2 up to n minus 1. So notice that there are n such roots of unity, and these roots are called the nth roots of unity. Okay, let's solve this problem. What do we have to do? We have to show that any complex number z, which satisfies the equation z to the power n is equal to 1, can be captured in this manner. So in order to do that, let's analyze the equation itself. Consider z to the power n equal to 1. Taking the absolute value, what do we have? We have then absolute value of z to the power n is equal to the absolute value of 1, which is equal to 1. What do we know about the absolute value of z1 times z2? That's going to be the absolute value of z1 times the absolute value of z2. So this implies that mod of z to the power n is equal to 1. But then mod z is a real number. What are the real numbers whose powers will be equal to 1? It could be either 1 or minus 1. These are the only two possibilities when mod z is being considered. Real numbers whose powers are 1 is being considered. But then mod z is non-negative. It's the absolute value of a complex number. So this is a non-negative real number, and hence we have, since mod z is greater than or equal to 0, we have mod z is not equal to minus 1. Because of that, mod z is supposed to be equal to 1. That means z is on the unit circle. Z belongs to S1. Okay, let's see what happens when z is in S1. Z, then we can write z as e to the power 2 pi I theta for some theta belonging to 0 to 1. This is the polar representation of our complex number z. So let's write it in that manner, because taking the powers will become far easier in that scenario. And let's see what happens when z to the power n is equal to 1. This implies that z to the power 2 pi I n theta in this case, because the power is just going to get multiplied to the exponent, and that's going to be equal to 1. Oh, I'm sorry, this is going to be e to the power 2 pi I n theta is equal to 1. Now from trigonometry, this tells us that 2 pi I, or rather 2 pi n theta is equal to 2 pi k, where k belongs to the integers. This is precisely when e to the power 2 pi I theta is equal to 1. Theta will have to be an integer. In this case, n theta will have to be an integer. After cancellation, if you notice, this implies that theta is equal to k by n, where k belongs to integers. So this is first. Whenever z satisfies the equation z to the power n is equal to 1, z is on the unit circle, it is of the type e to the power 2 pi I k by n, where k is an integer. That much we have certainly established. But we still have a little more work to do. We would like to see that we don't want all the integers possible, right? The first observation is that, so notice that if L1 and L2 are such that 2 e to the power 2 pi I k, or rather L1 by n theta is equal to, theta is L1 by n in this case. If this is equal to 2 pi I L2 by n, what does this imply? This again, by a very similar argument, tells us after multiplying by the complex conjugate, this implies that e to the power 2 pi I L1 minus L2 by multiplying the complex conjugate, this is equal to 1. And by a very similar argument as above, this tells us that L1 minus L2 by n belongs to z. So in particular, if L1 is equal to L2 plus some k times n, then e to the power 2 pi I L1 by n is equal to e to the power 2 pi I L2 by n. We get the same number. And because of that, we would like to avoid these repetitions, and we will hence go modulo nz. So this is precisely saying that, right? If you go modulo nz, you'll capture all the roots of unity. Write that down. Hence, every element of the type every complex number z such that z to the power n is equal to 1 is now given by e to the power 2 pi I k by n, where k is equal to 0, 1, 2 up to n minus 1. Notice that if k is any other integer, we can write it by a Euclidean division. We can write, let me just write it in brackets, any other integer d can be, or rather L can be written as L is equal to d times k, sorry, d times n plus k, where d is some divisor and k is the remainder, where k is in 0, 1, 2, 3 up to n minus 1. K, notice that since L and Dn are integers, k is also going to be an integer. And by using this division algorithm, we have every root of every element, every complex number which satisfies z to the power n equal to 1 can be written in this manner for k from 1 to n 0 to n minus 1. I will leave it as a check for you to come up with an argument to establish that e to the power 2 pi I k 1 by n is not equal to e to the power 2 pi I k 2 by n for 0 less than k1 less than k2 less than n. For two different such integers, they will be distinct elements. So this gives us, hence we have concluded that z to the power n equal to 1 has n distinct roots given by e to the power 2 pi I k by n, where k is ranging from 0, 1 to up to n minus 1. These are called the roots of nth roots of unity and are called the nth roots of unity. In the next problem, let's try to extend what we just did to a general complex number. Instead of looking at nth roots of just unity, let's take an arbitrary complex number w and just check what can be the possibilities of z to the power n equal to w. We have done all the hard work. We will just use the arguments used earlier to just establish this as well. Show that if w is a non-zero complex number and n a positive integer, then there exist n distinct roots of the equation z to the power n is equal to w, and any two such roots differ by multiplication by a root of unity. Any two roots differ by multiplication by a root of unity. Okay, let's see what happens. I'll just rush through this proof because the idea has already been developed. Z to the power n equal to w. This is what we would like to consider. And w is in the polar representation given by r e to the power I theta for some fixed r and theta. In polar coordinates, w, let w be equal to r e to the power I theta for some fixed r n theta. Then if z is again the similar, by a very similar argument, mod z to the power n will be equal to mod w, which is equal to r, and we know that there is exactly one positive nth root of real number, which is the nth root of r. So this gives that mod z is equal to r to the power 1 by n. This much is certainly clear. And if z is now equal to r to the power 1 by n, say e to the power I times phi, this tells us that maybe 2 pi I phi, I should put that 2 pi, let me put 2 pi so that I have to worry only about the interval 0 to 1. So let me put a 2 pi phi here, and then we have z to the power n is equal to w implies r to the power 1 by n e to the power 2 pi I phi to the power n. This is equal to r e to the power 2 pi I theta, and by a similar argument, r is a positive number, so r to the power 1 by n to the power n is equal to r, and the r's cancel. This gives us that e to the power 2 pi I n phi minus theta is equal to 1. I have already multiplied by the complex conjugate of e to the power 2 pi I theta on both sides, and we will be able to write it in this manner. This gives us that n phi minus theta is equal to some integer. That's exactly like in the previous case, and which tells us that phi is given by theta plus k by n, where k belongs to integers. Let me just summarize what we have. Hence, z is given by e to the power 2 pi I theta plus k by n, where k belongs to the integers. And this is again given by simplifying it, this is e to the power 2 pi I, r to the power 1 by n is also there. 2 pi I theta by n times e to the power 2 pi I k by n. So notice that again, for I will just directly write here that k is now ranging from 0 to n minus 1, because other values of k will coincide with one of the n values given here. Okay, I will just leave it to you to check that if you take a root of unity and multiply it by if you take an nth root of unity and multiply it by another nth root of unity, you get back another nth root of unity. Check that product of two nth roots of unity is again an nth root of unity. So is its inverse. And the inverse of an nth root of unity is again an nth root of unity. Basically, I'm just writing that the nth roots of unity form a group. By using these two facts, you should sit down and check this. By using these two facts, it's quite straightforward that any two roots of the equation z to the power n is equal to w differ by multiplication by a root of unity. On the complex plane, we are quite familiar with the notions of circles and straight lines. However, the circles and straight lines till now have been kept as different entities. The next problem is an attempt towards giving a unified expression which captures both circles and straight lines at the same time. These are called generalized circles. Let me write down the problem and elaborate a bit more on that. This is the problem 4. Let W1 and W2 be distinct points and lambda be a positive real number. So the first part of the problem tells us that the set given by set of all z such that the absolute value of z minus w1 by the absolute value, maybe I should write it in this manner, by the absolute value of z minus w2 equal to lambda gives a circle when lambda is not equal to 1 and a straight line when lambda is equal to 1. Let me just write a converse as well. Conversely, every circle can be written in this manner. In fact, every circle and straight line. I'll not give a detailed proof of the converse. The converse is basic Euclidean geometry. I'll just give you an indicator. The first part, however, let's try to solve completely. The problem tells us that if you look at the set of all points z such that mod z minus w1 by mod z minus w2 is equal to lambda, that will be the equation of a circle. We are familiar with the equation of circle in the form of z minus a, absolute value of z minus a equal to some r, where r is the radius. So this is going to be the circle of radius r around a. This problem tells us that 1 captures exactly these type of circles, and 2 tells us that every circle can be written in the manner stated above. So let's focus on the first part. Consider the set of all points z such that mod z minus w1 by mod z minus w2 is equal to lambda. So remember that lambda is a positive real number here. So if you multiply by looking at the square here, we get mod z minus w1 square is equal to lambda square times mod z minus w2 square, which will be mod z square minus z w1 bar minus z bar w1 plus mod w1 square. Remember that absolute value of z minus w1 is equal to the square of the absolute value of z minus w1 is equal to the product of z minus w1 with its conjugate, which can be expanded out in this manner, which will be equal to lambda square times mod z square minus z w2 bar minus z bar w2 plus w2 square. So let's first consider the case when lambda is equal to 1. What happens if lambda is equal to 1? The mod lambda square cancels off, and we can write this as z times w1, or rather w2 bar minus w1 bar plus z bar times w1 minus, this is going to be z bar times w2 minus w1. This is equal to mod w2 square minus mod w1 square. I leave it to you to check that this can be written as alpha z plus alpha bar z bar is equal to c, where c is in R, and should sit down and check that this is exactly capturing the equation of a straight line in the complex plane. Let's consider the case when lambda is, which is a real line, which is a line. Okay, let's consider the case when lambda is not equal to 1. When lambda is not equal to 1, let's see what we have got here. This is the equation we have after expanding it out, and that can be written as 1 minus lambda square times mod z square minus z times w1 bar minus lambda square w2 bar minus z bar times w1 minus lambda square w2, which is equal to lambda square mod w2 square minus mod w1 square. Let's divide by 1 minus lambda square to get mod z square minus alpha times z minus alpha bar times z bar plus mod alpha square. Let me write it down so that I can complete it into squares. This is equal to lambda square times mod w2 square minus mod w1 square by 1 minus lambda square plus mod alpha square. So the left hand side is going to be equal to mod of z minus alpha, and I'll just leave it to you to check. What is alpha here? Alpha is basically w1 bar minus lambda square w2 bar by 1 minus lambda square, and you should check that the right hand side also does such. Okay, I'm making a mistake. There is no brackets like this here. This is going to be equal to lambda square times w2 mod w2 square and something. So this is going to be r square, where r is some real number. I'll leave it to you to check that this is indeed equal to this quantity which I am putting down in green. That's indeed going to be equal to some r square. Let me not spend time trying to prove the converse. Let me just say that the converse is some Euclidean geometry that has to be worked out, which I will leave as an exercise to you. It's not complicated. One just has to sit down and find out the right theorems from Euclidean geometry to prove the converse. Let's now do a problem on complex derivatives. Let's take a polynomial and prove that the roots of the derivative of the polynomial will be on the convex hull of the roots of the given polynomial. Let me just define in that case what the convex hull of a set in R2 will be. Let A1 to AN be points in C. In fact, we can define this in Rn, but let me just focus on C because that's all we need. We say that, okay, the convex hull of A1 to AN is given by the set of all summation lambda I ai, where lambda i's are positive real numbers, summation lambda I less than or equal to 1. So if you start off with, say, for example, 2 points, the equation here will tell us that we are considering all the points which lie on the straight line joining A1 and A2. Suppose this is A1 and A2. This is exactly what it does. And if it is 3 points, then it will be all the points which are lying in the interior of the triangle which connects these 3 points. A similar description can be given. It's basically the convex polygon, the polygon which has AIs as its edges, the closed convex polygon which contains AIs as its edges. So that's precisely what the convex hull of this set A1 to the points A1 to AN is. In the next problem, we will try to relate the roots of the derivative of a polynomial with the roots of the polynomial itself. Let me write down the problem for you. This is problem 4 or 5. 5. Let P of Z be the polynomial given by P of Z equal to C times Z minus Z1 times up to Z minus Zn. So Z1 to Zn are roots of the polynomial P, where Z1 to Zn are complex numbers, not necessarily distinct. Notice that z1 to zn are precisely the roots of the polynomial p. The problem here is to show that then the roots of p prime of z lies in the convex hull of z1 to zn. So to do this, the first thing that we will have to, let's give a solution to the problem. The first thing we will have to do is to consider the product rule, the Leibniz rule, which we know works on the product of functions. When you consider the complex derivative, and by product rule or the Leibniz rule, p prime of z is given by summation okay, let me write it this way. Summation j is equal to 1 to n c times z minus z1 z minus zj. Let me put a hat here to denote that it has been removed, up to z minus zn. This is precisely the derivative by the product rule. The hat here indicates that this term does not appear in that particular, this particular linear factor does not appear in that particular term. All right, now at points, this is also a polynomial of degree n minus 1. At points away from the roots of p, we have the rational function p of z by p prime of z, or rather p prime of z by p of z, given by summation c times, so let me just write the c out, z minus z1 up to z minus zn with the z minus zj hat here, divided by p of z is basically c times z minus z1 all the way up to z minus zn. And this is nothing but summation j equal to 1 to n 1 by z minus zj. Let us now consider the roots of p prime. Let w be a root of p prime of z. If w is one of the roots of p of z, then we don't have anything to prove because it's already in the set of roots, which in particular is a subset of the convex hull. So we don't have anything to prove extra when w is already a root of p of z. So let's assume that w is not a root of p of z, such that p of w is not equal to 0. Then if we plug it into the equation above, this equation, let me call this star, then by star we have p prime of w is 0, p of w is not equal to 0, and therefore summation 1 by w minus zj, this is equal to 0. But then we are almost through, because now we will just rewrite this as w bar minus zj bar by absolute value of w minus zj square is equal to 0, where j is going from 1 to n. Yep. Now we are almost done. We just have to write the equation properly. This tells us that summation w bar, let me write the w bar outside here, w bar times summation 1 by mod of w minus zj square, this is equal to summation zj bar by w minus zj absolute value square. Let's now take the complex conjugate. We could have started off with the complex conjugate and then worked, but that's okay. We'll take the complex conjugate here. And that tells us that, let me just write down, after taking the complex conjugate, this is equal to summation 1 by mod w minus zj square by summation 1 by mod w minus zj square. This times zj. So let's call this to be equal to, say, lambda j, and it's a simple check to see that summation lambda I is equal to 1 and mod w is equal to summation lambda I or lambda j zj, proving that w is in the convex hull of z1 to zn.